In this video and the next few, we will be talking about the Smith chart. The Smith chart is a graphical tool that can solve transmission line problems. Is very helpful in design as well as visualization of what's going on in RF or transmission line problem in general. Modern equipment still have displays in Smith chart, so let's get started. The Smith chart is simply a graph that describes the mathematical relationship between the normalized impedance and the reflection coefficient. So if we look at this equation, the highlighted equation 2.101, we'll see on the left hand side here is the normalized impedance. The impedance as a function of position, whether the coordinate is z or d. Z is a coordinate measured from the source to the load, while d is the same position function measured from the load to the source. All right. So z as a function of position divided by the characteristic impedance, the normalized impedance that is, which we refer to as z sub n, is equal to 1 plus gamma divided by 1 minus gamma. The other equation, which is actually the inverse of that, or rewriting that as gamma in terms of z, it says simply that gamma at any location is the difference between z minus z naught divided by z plus z naught, or z normalized minus 1 divided by z normalized plus 1. This equation is complex. All right, each quantity here, z and gamma, has a real and imaginary components. So z normalized is simply r plus jx divided by z naught, or can be written as lowercase r plus j lowercase x. All right, that's the real part of the impedance function, and that's the imaginary part of the impedance function. Gamma likewise has again a real component, gamma real and gamma imaginary. So manipulating these equations here, all right, to separate the real part and imaginary parts from each other so we can end up with real equations, we will conclude these two equations. An r is equal to 1 minus gamma real squared minus gamma imaginary squared divided by a denominator here, and the x is equal to that. Now going from here to there is really straightforward. All what you need to do is try to take this complex ratio here and separate it into real plus imaginary, and then equate the real to the real, imaginary to the imaginary. It shouldn't take you more than 5 minutes if we sit on the side here with a piece of paper and a clear mind and do the development. So if we manipulate these two equations here, we can rewrite them in this format. These formats here are famous formats for the equation of a circle. Here's the general equation for a circle in the gamma real, gamma imaginary coordinate system. So I'm just going to move down here, and here's my coordinate system now. Gamma real here, gamma imaginary there, gamma real there, gamma imaginary there, and I have two equations, so I'm mapping each one of those separately here. So let's look at the top equation here. Gamma real minus some shift, all right, on the gamma real axis is going to be the location of the center of the circle. Here it is. So the shift is r over 1 plus r. Here it is, r plus over 1 plus r. That's the displacement on the horizontal axis. On the vertical axis, there is no displacement or there's no shift, so the center is right there on the gamma axis, gamma real axis right there. That's the center of the circle. The radius is right there. That's the radius. 1 plus r in the denominator. 1 over that is your radius. 1 over 1 plus r is the radius. So this here is a map of this equation here. All right. This graph here is basically a map of this equation. And this graph is likewise a graph that represents this equation for the x values. R and x being the real and imaginary components of the normalized impedance of the line at any location. So that represents the r, constant r circle, and this represents a constant x circle. With r and x being variables along the transmission line as functional position, then we expect r to vary, and therefore the position shift is going to vary and the radius is going to vary. And here is an example of different r values, all right, and the corresponding circles. For example, if you do r is equal to 1, r is equal to 1, that's 1 divided by 1 plus 1, that's 1/2, and the radius is again 1/2. So that circle here will have a radius of 1/2 and shifted by 1/2, and that's how it ends up to be. The radius is right here, 1/2. I'm sorry, the center is 1/2, which is going to be right here, and the radius is 1/2, so it will end up at 1 here, and the other point there will be a 0. All right, so you can substitute different values and figure out for yourself that these circles actually represent different values. If I put r is equal to 0, then the shift of the center is going to be 0, so that means the center is going to be here, and the radius is going to be 1 over 1 plus 0, which is 1, so the radius is going to be 1. So this bigger circle here is radius 1, and shift is 0, so the center is right at the origin here, and the radius is 1, and that's your big circle of r is equal to 0. All right. Likewise, we can do the same thing for x, different x values. Here they are. These are all different x values. X being the reactance is going to be expected to be either positive or negative, and therefore you can have circles on top and circles on the bottom. The circles on top will have positive x's, and the circles on the bottom will have negative x's. At this point, we'll switch the presentation to a different file where I can do some animation. This graph displays the R circles and the X circles. The R ones are the left here in black, all the way from 0 to infinity, and the X circles here in blue. If you start the positive x from 0 to infinity, you go this way. If you go the negative x from 0 to minus infinity, you go that way. And the two are displayed versus gamma real on the horizontal and gamma imaginary on the vertical. Same thing here, gamma real, gamma imaginary. So we can just put them on top of each other. And in this diagram here, we did exactly that. It's cluttered with so much writing, so let's just clear the writings in here. These are the two sets of circles. All right. Typically, we deal with passive resistance between 0, a short circuit, all the way to infinity, which is an open circuit. So our circles are mostly the ones that you see right there. If you are talking about active devices, they produce negative resistances, and those negative resistance will correspond to circles in this region out here. So if we limit ourselves to passive resistance, this region here is unnecessary to show in our Smith chart. We don't need that part. So we can just erase all these lines outside the R is equal to 0 circle here, which we are going to do just right now. As you can see now, the R circles from 0 all the way to infinity, and the X circles are truncated within that region. No other lines are out there. If we ever need them, we can always reproduce them and work with them. This is a typical Smith chart that you will see in books and publications and screen displays of measurement equipments and computer simulators. So here's an example of commercial Smith chart overlaid on the one that we just developed. Okay, you can see that it will have a lot more details that enables the user to be precisely or more accurately locate a given R and a given X. All right. Now, as you can see, this chart doesn't have the real and imaginary axes, which used to exist like that. So we have to keep in mind that part, although it's not really displayed on the chart. The chart has many other scales, as you can see around, and also scales on the bottom that enable you to evaluate certain things, and we will explain these scales a little bit later. All right. Now let's explain those scales that we have on the Smith chart. All right. To do that, I'm going to have a split display here. On the right is the lecture material out of lecture 7, and on the left is the Smith chart without the scales yet. All right. basically I just superimpose the coordinate system, which is gamma real and gamma imaginary. All right. Now, to explain those scales, we need to understand what we're going to do with this Smith chart. Basically what we do is we have a given impedance, all right, a location on the transmission line. Okay, so this is a given R. The circle is right there. I'm not showing the whole circle, I'm just showing part of it. And this is a given X circle. And the intercept is the location where R is equal to that much and X is equal to that much. In other words, that's the impedance of that given value. These are normalized values, don't forget. Now, this point here on the gamma scale represents certain coordinates. All right, gamma real would be the distance between this point and the vertical axis, and gamma imaginary would be the distance between this point here and the horizontal axis, and therefore the line connecting from here to there is our gamma. All right, let's connect that line. Here it is. So this is our gamma phasor. That gamma phasor here has a magnitude and an angle. All right, the angle is right there, and here's our first scale that we will be using or will be describing. The scale that will start here as a 0 angle and goes all the way to 180 degrees plus or minus, so we have the negative angles on the other side. So the first scale that we are talking about here is the phase angle of gamma, goes from 0 to plus or minus 180 degrees. In the notes it's actually number 2 right there, the phase angle of the reflection coefficient gamma scale. All right. Now, so what we need to do is not just connect this point to the origin, we extend that line out there and read the angle on this scale here, which is actually the angle right there. If you read this angle here, it just happens to be about 72 degrees for this particular choice of location. So that's your angle. Next, you need to find out what's the magnitude of that. To get the magnitude, what we do is draw a circle that passes by this point, like this. And now we look at the radius of that circle, which is the same as the gamma magnitude itself. That radius here is a portion of the radius of the R is equal to 0 circle. Remember, this R equal to 0 circle, and the radius of that's supposed to be unity. So the radius here is actually a portion of the 1, and a scale is given to us at the bottom here from 0 to 1, which is the big circle. All right, and the projection of that on a linear scale gives you about 0.76. So the gamma magnitude is 0.76. So we can say that this particular point, the impedance that we have, correspond to a gamma of 0.76 magnitude angle of 72. So now we learn about the magnitude scale, and here it is on the lecture 7 notes, the magnitude of the reflection coefficient gamma scale. Right. So these are two scales here that we already saw, the magnitude and the phase angle of gamma. Okay, the next scale to discuss is the normalized distance moved scale. Normalized distance moved scales. The idea here is, if you know gamma at some location, you can always relate it to gamma at some other location because of this equation right here. Gamma at any location is equal to the ratio between the minus wave over the plus wave. Gamma at some other location is going to be the same ratio. So if you ratio these to each other, you can get gamma Z2 relative to gamma Z1, and here it is. Gamma Z2 is equal to gamma Z1 e to the 2 gamma Z2 minus Z1. All right. So the two gammas here are related to each other, and the distance moved from one location to another. And that's the scale here that we're talking about, the normalized distance moved scale. Why it's normalized? Because we are going to work these as ratios to the wavelength. We're not going to work them in meters, and you will see that in a minute. So we take that expression, and then we express the gamma in the exponent here, which is the propagation, the complex propagation constant, into an alpha and beta. So the magnitude of gamma Z2 is the same as the magnitude of gamma Z1 e to the 2 alpha Z2 minus Z1 right there. And the angle of gamma Z2 will be the angle of gamma Z1 plus the angle of this part here, which is related to J beta. So the angle of gamma Z2 equal to the angle of gamma Z1 plus 2 beta Z2 minus Z1. Looking at this expression here and substituting beta as 2 pi over lambda, we end up with 4 pi over lambda here because that's 2 beta, 4 pi over lambda, and we have Z2 minus Z1. So Z2 minus Z1 over lambda, that's the normalized distance moved, right? Ratio between the distance moved and the wavelength multiplied by 4 pi. So now we read this expression again. The gamma magnitude changes as determined by the distance moved and the attenuation coefficient. The angle of gamma changes by 4 pi times the normalized distance moved. If I were to ignore the loss, attenuation coefficient alpha is equal to 0, e to the 0 is equal to 1, that means gamma Z2 is equal to gamma Z1. That means as I move on the line, my gamma magnitude doesn't change. However, the angle is going to change. If Z2 is greater than Z1, that means the angle is going to be increasing. If Z2 is less than Z1, that means the angle is going to be decreasing. So my gamma phasor here is going to rotate around this constant circle because constant magnitude, and this angle is going to be changing. So if I move from Z1 to Z2, I can calculate the angle, and I can use this scale here to determine where is the new location. However, I can also just use the delta Z over lambda and create a new scale based on this. And that's what we are talking here about, the normalized distance move scale. Let's look at that scale and see if we can explain it and understand it. Here it is. This is the scale that we would call the distance moved over lambda. Alright? Now, if you go back to this equation here, if I move a full wavelength, that means a change of angle of 4 pi, that means 2 rotations around the chart. If I move half a wavelength, that means 2 pi, that means 1 rotation. If I move a quarter wavelength, that means 1 pi, that means I move 180 degrees. And here it is. If you look at this number here, that's 0, and a quarter corresponds to 180 degrees. So this is actually a quarter wavelength. So these numbers here are calibrated in a linear fashion, in a linear scale, to go from 0 to a quarter wavelength, and that corresponds to 180 degrees. If I were to continue, that would be 0.5 wavelength. That's a full rotation. Again, half a wavelength gives you 2 pi. Half a wavelength gives you 2 pi. So let's look at the scale and decide what does this scale correspond to. It's a linear scale that goes from 0 to 0.5 in this direction and corresponds to a decreasing angle because the angle increases this way. So this corresponds to a decreasing angle. That means this is a negative change. That means my Z1, the initial location, is greater than the final location. And if Z is greater initially than the final one, that means I'm coming closer to the source. So this scale here corresponds to motion on the transmission line towards the source. So here we go. We label this one here as motion towards the generator or towards the source, which corresponds to a decreasing angle. Now, if I was moving the opposite way, that means those numbers here are going to be backwards. And just like the way you calibrate a ruler, sometimes you calibrate it both ways, so you can use either end to measure things. We are going to do the same thing. We are going to add another scale that goes the opposite way. So as the blue scale increases this way, the red scale increases the opposite way. again, it goes from 0 to 0.5 in a linear fashion. It's an angle. And as we move this way, the angle is increasing. So the angle is increasing. It means Z2 is greater than Z1. And if Z2 is greater than, that means the final location is further away from the source than Z1 was. That means I'm moving towards the load. And here we're going to be labeling both of them, towards the generator or towards the source, towards the load. So here we go. We have a scale for motion towards the load and a scale for motion towards generator. Use whichever one is more convenient. So finally, here are the scales that we have discussed so far: the gamma angle scale, the delta Z motion, whether it's towards generator or towards the load, the magnitude of gamma scale. There will be other scales and other features of the Smith chart that we will be discussing in a later lecture.